In software engineering, we are discussing the software testing strategies. In software development, software testing is very important. That is, whenever we make a software, the software has to be correct. It has to be right. So any testing strategy, there can be multiple testing strategy. Every testing strategy has to incorporate the test planning, then the test case design, test execution, the resultant data collection, and then evaluation. So two things have to be together, flexibility also and rigidity also. But these two are, antonyms. Flexibility means these testing strategies should promote a customized testing approach. And rigidity means there has to be a reasonable planning and management tracking as the project progresses. That is, a blend of flexibility and rigidity in any kind of testing has to be promoted, has to be there. So this is the different way, and most of the time we have the unit testing followed by the integration testing, followed by the validation testing, and finally the system testing. And these all are based on certain software development lifecycle phases. A strategic approach to software engineering. So there are different testing strategies, but all of them, or mostly all of them, they provide a template. They provide a way for testing, and they all have certain general characteristics, attributes. The first thing is, we need to conduct effective technical reviews. We are just not going to code, doing the static and dynamic analysis. Before that, we are interested in technical reviews. These people will sit, the expert will sit and will see your work. And from the requirement, design, the construction, everywhere the technical reviews should be there. And because of these technical reviews, most of the error which you are going to find in actual testing, they are eliminated, they are fixed. Testing always start with the basic level to the advanced level. That is, it will start with the component level. I am talking about a component. It can even be a function, small function. It can be a component, it can be a class. So then this testing goes outward towards the integration of the entire system. So different testing techniques are there, but they are appropriate, they are suitable for different software engineering approaches and at different points of time. So there is no hard and fast rule of any testing. People say we do white box testing, black box testing. So testing is conducted by the basic level, the initial level. It is always tested by a developer who has developed the software, the team, development team. And then if you're talking about the large products, there is an ITG, independent test group. They also get involved. So all of them, they together, they make the testing work. Testing and debugging. These are different activities, but related activities. That is, testing is to find the error. Debugging is to fix the error. So debugging must be accommodated in any testing strategy. So testing cannot just be done by you need to debug also. A strategy of software testing, as I said, it will start with the low level, component level, even the small source code segment, that it has been correctly implemented, it has been correctly coded, and also the high level test, where we have majority of different systems, they are coming together. So validation will be done against the customer requirement. We'll talk about the verification and validation just now, but just not finding the semicolon. But whatever has been done, are they showing these customer requirements? Are they being made with reference to the customer requirement? Are they traceable to it? Verification and validation. Now in software testing, these two are very important ones. First of all, the software testing is one of the element of verification and validation. And verification and validation is one of the element of the software quality assurance. Software testing, software quality assurance. So, verification is whether software correctly implements a specific function. That is, if you have made something, is it working correctly? This is verification. Validation is what you have done, does the user want? That is, whether a software is traceable to the customer requirement. I'll give an example. Let us say we have written a function as a developer, add a plus b equals c. And if it is producing the result correctly, c is giving the result of a plus b, that is, verification has been done. But user actually wanted subtract and you have given him add. So validation fails because user wants something else. You have given him something else. Though add and subtract function, even if you are giving them, they are working correctly. If you check it, it is verification. But maybe they don't want any of this. They would want multiplication. So Boehm, he states, the verification is, are we building the product right? That is, have we done enough work that the functions are working properly? Validation means, are we building the right product? That is, whatever user want, are we making for him? So this is a kind of Venn diagram. How does this verification validation relate? As I said, they are coming under software testing, which is coming under the software quality assurance. So the customer acceptance test and the usability test, all is the requirement of user. So am I building the right product? This comes under validation. In validation, am I building the product right? For that, we have to check the unit testing, then the integration testing, the various testings are there. And if you combine them, there is an in-between which belongs to both of them, regression testing, system testing, beta testing. In fact, beta testing and alpha testing, they are done with the users only. In the software development lifecycle, we do the requirement, then we design. That is, we first design system design. Then we do the architecture, that is the overall structure of the software. Then the module design. And finally, we code. So the unit testing, it validates the module component level. It will validate it. The integration testing will validate the architecture design. The system design will be validated by the system testing. And finally, the requirements will be validated by the acceptance testing. Verification and validation. The verification verify the intermediate products like the SRS, like the design documents, like the ER diagrams, test plan, traceability matrix. And these are done with the developer point of view, because as a developer, we are verifying what we have done is done correctly or not, or some independent team. They will see what the developer has done is correctly or not. We will verify without executing the software code sometimes. So we'll do the techniques, informal, review, inspection, walkthrough, technical and peer review. In validation, this is the final end product, like the developed software or service or system. We need to validate it because it is from the customer point of view, whether his requirement has been fulfilled or not. So this is validated by executing the software code. So functional testing, system testing, smoke testing, regression testing and many more. So this verification validation, they include Basically, they are the part of software quality assurance. So there are so many activities which will be used for verification and validation. So it can be technical reviews, quality and configuration audits. It can be performance monitoring, simulation, feasibility study, documentation review, database review, algorithm analysis, development testing, usability testing, qualification testing, acceptance testing, and installation testing. So these are the software quality assurance activities done for verification validation. So the testing, you can say that it is the last defender. You can assess your quality. That is, testing can show you whether the quality is there or not. Because errors can be uncovered and can be fixed to make the quality better. But testing is not a safety net. That if you have done testing, the quality is good. You can't test in quality. What does it mean? If before this quality was not there, after also testing there will not be the quality. So Miller relates software testing to quality assurance. He gave a very good, you can say, bridge. He said the underlying motion or motivation of program testing is to affirm software quality with certain methods that can be economically and effectively applied to both large scale and small scale system. Those methods which we use in any of the project so that we can ascertain the quality. Organizing the software testing. So most of the time the developers are asked to test the software. Now the user is not there right now, but developer has made the software. But developer, they may have their vested interest because they would like to show that they have done a good work, the program is error free, they have done exactly according to the customer requirement, they have completed the work on schedule, they are doing it under a budget. You know, everyone has to have an appraisal sometime. So developers, you can say most of the developers think that the software is their baby. So they would like to protect it. And they would like to show that what we have done is good. But testing is inherently destructive. Someone would, or testing would, try to destroy the software so that whatever points are there can be uncovered. So if error are present, even if you keep your eyes closed, customer will definitely find them. So whenever you are doing this testing, there are certain misconceptions. What are these? Developer should do no testing at all. This is a misconception. In fact, the unit testing is done only by developer only. Developer should do no testing at all. That is not there. Even if you are working in, say, Visual Studio and integrated development environment is there, you will use a debugger. You will use the, some breakpoints. You are doing testing as a developer. Second thing is software should be tossed over the wall to strangers to test mercilessly. That is, just throw it and let another people destroy it so that the errors can be found out. This is also not true. Testing is done to improve the quality, to find out the errors so that the customer doesn't get agitated or get upset. Testers get involved only when the testing steps are about to begin. This is also a misconception. Right from the requirement, from design, the coding, every time, everywhere, tester needs to be there. Because the test planning, the tester has to be there. The design, because most of the testing is done against the design, not against the code. Mostly people think that the coding is testing. No, it's not there. The requirement is also tested. Organizing for software testing. The software developer is always responsible for the basic level testing, the individual testing, the individual code testing, the component testing. For example, he has made a function, say add. Okay. He has made certain classes. Now this basic level testing will be done by developer only, the software team or the development team. Now developer also does most of the time the integration testing. That is a testing step that leads to the construction and test of the complete software architecture. Because when we go to the architecture, then the different team may come. So the unit testing and the integration testing, most of the time, because integration testing is the component are combined and then tested. Component testing is unit testing, component combined testing is integration testing. But once these testing are complete, then only an independent test group or some quality team or QA, QC will come. So the developer and the ITG independent test group, they would work closely throughout the software project because they want to ensure that the thorough testing has been done or thorough test will be conducted. So why do we want the independent test group? Because we want the freedom. There has to be someone which is not from the team, the development team. Then only the things can be uncovered. The problem can be uncovered. But the developer has to be available. Developer must be available to correct the errors which are uncovered. So ITG can be a part of a team. For example, there is a whole project team. So there will be an ITG team, that is quality assurance, quality control, the testing team you can say. And they are involved during the analysis and design also, planning and specifying the test procedures also throughout the large product. If the product is large, the system is going to be made which is large project. From initial to the end level, they will be involved. Because testing is all about checking every time. So checks has to be there. This is the ITG. This is the ITG role. So ITG reports to the software quality assurance organization if they are part of the team or they are an independent team. Achieving a degree of independence. So ITG is not reporting to the program manager or the software manager. They are actually reporting it to the quality team or quality head. The quality head will ensure that things are done correctly. The proper testing has been done so that the errors are uncovered and they are not propagated or they are not given to the user, because the user doesn't want, user want an error-free software. That is the whole quality aspect. Software testing strategy. Just see this spiral diagram. The strategy of the software testing, it can be assumed or viewed as a context to the spiral. Initial level, we develop small code, a component, class or a web app, content. So unit testing will be done. So unit testing is the basic testing, begins at the vertex of the spiral and it will concentrate and focus on each unit of the software as implemented in the source code. So we are checking here for the small component. Now it goes outward, from the vertex outward. So this goes to integration testing. Now the code component has been tested, they are combined and they are tested. So this is integration testing. So this focus is on design and the construction of the software architecture. So here the integration testing is done with respect to the design and the software architecture. Then we go again outward. Then we do the validation testing. And this validation testing, as I said, validation is done with respect to the requirement. So software requirement is the basis here. Then the system testing. Now the software, along with all the major system elements with which the software is going to work, are tested as a whole. So testing in software engineering is series of these 4 steps implemented sequentially. Initially, we'll focus on the component, ensuring that it functions properly as a unit, a component or a class or a web app content. They work as a unit. That is why the name is called as unit testing. I hope you got the idea. Because a unit is a small component. So when this component work as a unit, this one component, unit testing. So in unit testing, see, in your program you will write multiple if else, multiple while, do while, and switches, different kind of control structure will be there, if else, etc. So all the path need to be covered. Maximum error detection will only be done when you have the complete coverage of all the control structure. And next, the components are being checked. They are assembled. They are integrated to form a complete software package. They are like bricks. Components are like bricks, and they will make a wall. So these are combined. So integration testing addresses what? The problems of verification and the program construction. Because independently the module may work properly. What about combining them? Whether they work properly or not. So test case design, it focus on input and outputs. Because what you are feeding to your module, to your function, to your component, or to your component combined, what are the inputs and are you getting proper outputs? Validation testing is actually done against the software requirement specification. So this provides final assurance that software meets all function, behavioral, and performance requirements. So once this validation is being done, all the different system elements, it can be hardware, it can be people, it can be databases, or multiple things, a large product can have many. So once validation is done, these are all combined, all these elements, and then finally the last spiral you see here, system testing is done. So systems testing verifies that all elements, all system elements, they mesh, they gel properly, and they give overall system function or performance which is intended. Are they achieved? Most of the time, anyone in the software team or the novice in software field, they will ask, when are we done testing? What is the end point of testing? There can be multiple responses. The first response can be, you are never done testing. From your shoulder, the testing goes to the user shoulder. So the burden simply shifts from you, that is as a developer, to the end user. This can be a simple response. Testing is never ending. It goes round and round because people need change. People need they want to change your software. Another response is, if you have time, money, do it. When you are scarce of it, don't do it. There are certain approach, like the clean room software engineering. Now these kind of approach, they are suggesting statistical use techniques, and that execute a series of tests derived from a statistical sample of all possible program execution by all users from a targeted population. So people say that this is you can decide when the testing will end in this kind of approach. So you are 100% sure all the testing has been done in this clean room. We'll talk about that later. But this is how it is done. Tom Gill, he argues that the software testing strategy is going to succeed only when the testing department or the software tester does certain things. First is specify the product requirement, not in the worldly manner or running sentences. It has to be quantifiable before even the testing commences. The testing objectives, why you are doing it, what are your purpose, objective has to be stated explicitly. And the user, there are different user, experience, less experience, novice, or the user can be only a maintenance user. He will use sometimes your software. So the profile of each user category has to be fixed. And we have to develop a testing plan that emphasizes on rapid cycle testing. As I said, the testing cannot be completed. There is no end point. So a proper testing has to be done. and then build robust software that is designed to test itself. Actually, this is called anti-bugging. We'll talk about that. But a good software is which shows graceful degradation. Even if some problem is there, it will tell you this is the problem, and it can regain its motivation and work the way it was working, rather than killing your system. Technical reviews are very important, because you're just not do these dynamic analysis, static analysis. If someone is their expert, has already seen, there will be benefit. Conduct technical reviews to assess the test strategy and test case themselves. Testing is done to find the error, but there should be technical reviews to test the testing also. Test strategy, test cases have to be tested by they have to be tested again, and to develop a continuous improvement approach. For example, CMM levels, ISO levels. If you are not able to achieve that, but still try for continuous improvement approach, because that will make your software stable, that will make your company profitable. Software testing is one of the key software development life cycle phase. So we will be talking about the conventional software, that is web app and mobile app. We will not be talking about that more here. The conventional software, the traditional software, what we do, how do we test it? So there are various strategies, different strategies adopted by different software team, and the basic idea remains same. So what we can do is, first, let the whole component or a module or a system or a software is made, then we can test it. The second strategy is, what product, it can be a code, it can be a document, whatever is being done, test it, review it daily. So in real scenario, these two, because these two are very complementary, so we can combine these two. So most of the team, they adopt the good things about these two strategies. That is, some of the code can be allowed to be made and then can be tested, and some of the part can be tested daily. Unit testing in software engineering, or testing, verification, validation, is a phase, is a testing where we test a unit, a piece of code which work as a unit. That is why unit testing. So unit testing can be, you are testing say web content, you are testing a component, you are testing a function, you are testing a procedure, you are testing a class. If they are working as a unit and you are testing it, this is unit testing. Most of the time, the unit test cases are written and unit testing is performed by developers. So you are trying to check the behavior of the function or the class what you have implemented. So this is one of the basic testing, which every testing starts from here and it comes under white box testing. So unit testing is focusing on verification. That is, you want to test whether your software component or a module is working fine. The coding, the part, the construction you have done is what you have intended. And it is the smallest unit you can check. And in this unit testing, we do a lot of activity. For example, you have a function called add. Now this function, they may have, or you might have written number of control paths. For example, a lot of if else's, lot of while, do while, or switches. So there can be multiple control paths. In unit testing, all these control paths should be at least once be traversed. Okay? And second thing is boundary value testing. That is, for example, you have given 0 to 100. This is what you have to enter. But if the user enters 101, what will happen? So this is the boundary. So at the component level design, control path and the boundary value are tested in unit testing. These are the basic things. Along with this, whatever computation part or internal processing logic you have written, or the data structure you have used, say array or a linked list, how does it work? Does it work fine? For example, array always start with the 0 and with a number which is n minus 1. And because you are testing or checking the component on the basis of unit, you can conduct this unit testing parallelly. Whenever we are doing the unit test, there are certain considerations. Because as a developer, you need to know what you are going to do. First of all, there are modules you are testing. There are functions you are testing. And these modules are not working independently. They are going to work with some or the other component or the module. So the module interfacing is very important. How the data is going out, how the data is coming in. So as a program unit, the data inflow and outflow has to be tested. So interface has to be checked properly in unit test. Then whatever data structure you have used, because in a module or in a unit, you might be using the data structure which is local data structure. So you are using linked list or a stack or whichever. The data which is stored here or the data which is manipulated here should maintain its integrity. It should not be manipulated by itself. Then, because in a unit there can be multiple control flow path, it can be if else, it can be do whiles, it can be switches and many more. So all the independent paths should be exercised at least once, should be checked at least once to ensure that all the statements in a module have been executed, have been tested at least one for the expected result, what a developer is expecting. So these are different paths. Every path needs to be checked. The next part is the boundary value. Boundary conditions are always there because we want to limit or restrict the processing. For example, angle. Say example of latitude or longitude. Say example of latitude. The latitude always varies from 0 to 90 and 0 to minus 90. Okay, from the 0 equator to the north pole 90, to the south pole it is negative 90. If someone is entering 91 or 89.9, this boundary, because most of the software or the code fails at boundary conditions. So now this, whatever is happening, good is good. But if some error is there, some problem comes or user doesn't choose a scenario which the developer is expecting, there has to be some error handling also. So this error handling path also need to be tested. The error handling should be checked for error, and data flow across a component interface should be tested. If the data is not entering and exiting properly, the other tests are simply a moot. They are controversial. They are not to be believed. So interfacing the data going out and in, this is the basis of your unit testing, because ultimately this unit is going to be tested with other units. So the local data structure which you have used, it may be possible that when you combine it, when you go with it, there can be global data which may have some impact on the local data structure, and that need to be exercised, that need to be executed as a part of a unit test, right? So local data structure along with the global effect, this is also a part of your unit test considerations. The test cases, what you will write, what you will put here, these are designed to uncover errors due to certain erroneous computation. For example, if you have written A greater than B, maybe you should have written A less than B. So there can be incorrect comparison, there can be improper control flow. If you want the control flow to be like this, you have actually written in another way. These are the basis of the test cases for a unit test. Let me tell you, interface checking, local data structure, boundary conditions, independent path, error handling path, these are all the part of your unit test considerations. This is how you write the test cases. As I said, in unit test, boundary value or boundary conditions are very important. So boundary testing is one of the most important unit in unit testing, because software generally fails, your code will generally fail at the boundaries. For example, this is an array. Now, if you want this array, how are you going to define ARR array or some name and then 100? Now this 100 is seen. Now you will be tempted that 100 should be used somewhere or maybe, but the array It always starts with the 0 and it ends with 99. 100 will never be reached. What if someone or your program tries to access 100 or 101 or value which is beyond the scope of this array boundary? Okay. So that is the problem. That is, we need to check at the boundary. Most of the time, the repetition of loop, sometimes you are accessing the loop. You know that the loop should be like this, but maybe because of some error, you have exceeded the loop. So the number of times the loop is working properly, it is okay. When it goes beyond the scope, there will be an error. So the maximum or minimum allowable value, whenever it is encountered, it should be checked. I'll give an example. If you are entering an age and the limitation is 21 to 65. So there can be multiple test cases you are going to write. Invalid test case, if somebody puts 20, there will be an error. And it should show the error. Invalid test case should be 66 because it cannot go beyond 65. And the valid test case is in between them, like 21, 22, 65, 64. Under this unit test consideration, a good design always anticipates what are the error condition and what are the way to handle these errors. So there should be, normal code should be also included with the error controlling path. For example, 21 to 65. If your age, say, is, I'll just writing a code to check. The age is greater than 21 because 21 is included, so we'll put a equal also. Or you can write and also. Age is less than 65 because this 21 and 65 are inclusive, we will put a equals to sign also. Now this is a valid condition. But there has to be some error controlling also. If this is not done, what you are writing in error, in else, what you are writing, that needs to be checked also, because the error should be whether something goes wrong, it should be going to the reroute you have written, and the program should terminate very clearly whenever the error occurs, because error is not about about retry done blue screen. It's all about handling it properly. So Jordan says it as anti-bugging. Anti-bugging is all about identifying the error location, analyzing the actual error, prove the analysis, and cover the lateral damage, because error may create damage. You need to cover it also. That is anti-bugging. The code which normally does like this, good code. So if error handling paths you have implemented, the error has to be tested for its own error. So potential error to be tested when error handling is evaluated. Whenever you are testing the error handling, what can be the error in error handling? What are the potential errors? See, I'll give you one by one. Sometimes the error described by a developer is unintelligible. You cannot understand what the error is. Error noted does not correspond to error encountered. When the error is coming, is not at all the error you know that it ought to come. And the error condition causes system intervention prior to error handling. That means this error is not achieved before that some error has come. And exception condition processing is incorrect. You wanted to handle something else, but you have done something else. Error description does not do anything to assist the location of the cause of the error. It's all about finding the error. So if you're not able to locate, there's no point. These are the unit test consideration, because you have to check the error condition also for errors. Under the unit test procedure, unit testing is considered as an adjunct, as a help, as a party to the coding step. That is, whenever you are doing the construction, the unit testing is a part of it. They are considered to be adjunct to each other. So unit testing design can be done, or can be, because you are talking about test design, I'm not talking about testing. Unit test design can be done before the code, after the code. Both ways you can do. So unit testing is all about testing the code as a unit. So each test case should be coupled, or should know what are the expected results. So whenever you make a test case, there is a proper template. That is the brief, the test case, use case, the preconditions, the post condition, the error the exception handling. So you need to know what are the expected results and what is the actual result. So because a component is not a standalone program, don't think that if you have tested a unit or a component, everything is okay. Because it is not a standalone program. You are going to combine it with some of the other component. Maybe that component is developed, maybe that component is not developed. So a component is not independent. It will work with some or the other because the data flow and the interfacing will be there. So when we combine the module, there is a different kind of testing we do. But here, when we want to test a single component, we have to make for unit test driver and stub. Driver is what? Driver is the main program which is calling your module which is unit tested. That is, a driver is a program which is going to invoke or call your actual component you are testing right now as a unit. But this unit or this component may be invoking some other code also. So driver is a main program that accepts the test case data, passes these data to the component which you are testing actually, and it may give the result or print relevant result. This is the driver program you need to write for unit testing. Stubs are what? These are dummy sub-modules or sub-program, because these are the sub-program which are being called by your module being tested. So these are the modules that are subordinate or invoked by the component you are testing. So driver is the main program calling your module, and your module might be calling some other code which is the stub, right? So this driver and dummy are very important, and these are overheads because they are not doing any other work, but you are writing it in order to check a unit, a component or a module. So both must be coded, need to check for unit test, but you need to remove it before delivering the software. See, many components you may not be able to unit test because the making of overheads, driver and stub is not so easy. You don't want to make it either. So testing can be postponed. Sometimes the testing can be postponed until the integration testing, when the drivers or the stubs can also be used. Maybe you won't be using, or these drivers and stubs are already ready. But sometimes you need to postpone it also. Most of the time people make the driver and stub and then test their component. Integration testing. First of all, we have done the unit testing for a unit, a component or a module. Now we need to combine them and see whether they work in coordination, in collaboration, together. So this is module 1, module 2, module 3. We have already done the testing, unit testing we have already done, but now we are combining them. When we are combining them, we need to test whether they are working fine in combination. A new person or novice, a new baby in the software field will ask you a question, definitely, or he or she will have this question in the mind. The question is, if these components you have already tested, they are working fine, why do you have a great doubt that when you combine them and then test, they will not work together? Why you have this? Because everything has been tested. When you combine them, why they are not working? Why do you need to test? The problem is interfacing. Because one dancer is very good, the other dancer has won the America's Got Talent, the one has won the Britain Got Talent, and other also is a super dancer. When they are dancing together, are they synchronized? Are they looking good? Are they dancing so that they get the prize? No, it is not always like that. So the interfacing is a problem. Data can be lost across an interface. Interface is all about how these two modules or multiple modules connect. One component can have, I'm not saying always, inadvertent adverse effect on another. There are sub-functions, when we combine them, they may not produce the actual work which we want, desired major function. And if you have some error, say, I'm taking just a number to explain you, 0.1, 0.1, 0.1, and you say, oh, okay, it is acceptable. When you combine these all modules, maybe these 3 modules we are combining, it gives you an error of 0.3, and you are being told that 0.25 is the acceptable limit. So individually acceptable imprecision magnified to an unacceptable levels. This can happen. And global data structure, because now when you combine these, you are working with local data structure in unit testing, but now you're working with global data structure. These may present certain problems. So integration testing is a systematic technique for constructing the software architecture and conducting tests for the interfacing. So integration testing is for interfacing. For example, I'm making just an architecture. This is how the architecture is seen, where the different components will be put and overall structure of the software can be seen. So we have modules A, B, C, and we place it where it belongs. Now check for the interfacing. Check for all the problems I just mentioned you. Then it is integration testing. Individually they may work, but in a combined way you need to recheck. In integration testing there can be 2 ways. Most of the time in the initial era, people would combine all these units or modules or component together, one at another, all combined, and then test them as a whole. As the Big Bang approach is the way to test the modules as a whole, not individually, not in a combined way, one by one. But you are checking, combining it, and you are saying we have integrated and doing the Big Bang approach. But there will be chaos, because now the errors once you are encountering, the correction will be very difficult, because the problem where it has come, the location, the isolation of the cause is not even complicated. It might be impossible sometime because everything is combined. So the best way is to use the incremental integration. What does it mean? We take one module, combine it with some subordinate module, and then check for the integration testing. When it is done, we simply add one more or few more and then check for the interfacing and other problems we mentioned. So program is constructed and tested in small increments, because now here the errors are easier to locate, easier to isolate and correct. So interfaces are tested completely when you have the incremental way of adding the modules and then checking components and checking. So this is a systematic test approach that may be applied, and this should be applied. Integration testing. So integration is all about combining the component, the modules, and then testing. Let me tell you the bifurcation. First of all, we have integration. It can be divided into incremental integration testing and Big Bang integration testing. Big Bang is all about combining all the modules and testing all the modules at once. Incremental means adding one by one, incrementally, and then finally making all the modules combined one by one and testing in each step. So it can be bottom-up approach, we can apply top-down approach, and there is a sandwich approach also. So in integration testing, there are various different incremental integration strategies. So how do we do it? Let us start with top-down approach. As the name is suggesting, we'll start with the top. One by one we'll go to the direction which is vertically downwards. So an incremental approach for the construction of software architecture. That is, here we are more focused on the architecture, how these modules are there or the components, and then we combine them one by one. So modules are integrated or added by moving downward in this figure from top to down vertically through the control hierarchy. The top one is the main program, beginning with the main control module. We are calling it as a main program. So modules, the subordinate modules to the main control module are incorporated. So you can choose any method, depth first or breadth first. In the top down, you can either have depth first and breadth first. Depth is top to down, breadth is from left to right, subordinate. So depth first integration, it integrates all the components on a major control path of the program structure. So here comes the software architecture. So we'll start with the top and you will go directly down, that is vertically down. But which major path you will choose is arbitrary. That is, it depends totally on your application. These are application specific characteristics. I'll tell you an example here. See, here certain blocks are there which are modules, which are components. So selecting the left hand path, the components, what we are going to add, will take the M1 first. I'm talking about the top down, then M1, then we are taking the depth first integration. So you can take any of these, but this depends, this is arbitrary. So M1 you start with, then you have to add M2 because this is top down and depth first integration. Then you have to go down. Either you can take M5 or M6. This is again application specific. But if M5 is dependent on M2 or M2 is dependent on M5, then you have to take M5. So you'll start with M1, go to M2, then you will add next as M5. Finally, because there is only M8 is only there, so you'll add M8. Right? Okay. Then after that, you have to add M6. In M1, you have three choices, M2, M3, M4. In M2, you have two choices, M5 or M6. Because this is depth first and top down, the chain will be M1, M2, M5, M8 first. Then we'll take the central one, that is the M1, M3, M7. Then we have to take the M4, that is M1 and M4. M1 is already taken, so then you have to take the left, middle and right in the depth first manner. How about the breadth first? So in this top down, we went from top to bottom. Depth first, we took the first one, vertically we came down. In breadth first, we have to take from left to right, that is horizontally. Horizontally means when you take M1, after you take M2, you will not take M5 or M6, you will take rather M3 and M4. So it incorporates all components directly subordinate at each level. So in the first case, what we saw M1, M2, M5 and M8. But here, because this is breadth first, so we'll not go to the depth, but rather we'll go to the breadth. Okay. At same level, subordinate modules we have to take. So we have to move across the structure horizontally. In depth first, we went vertically. How do you take it? Let us take the example from this figure only. So the component, because M1, after that what you are going to take? M2. And since M2, M3, M4, they are in the same breadth, so you have to take M2, M3 and M4. This is what you have to take. Then you have to go to the next level. This is again the next subordinate level. Then you have to take M5, M6 and M7. Finally, you have to add MA. So integration in these cases are performed in series of certain steps. Mainly the 5 steps we have. So how do we do it? The main control module, that is the main program, is used as a test. This is a driver, and stubs are substituted for all components directly subordinate to the main control module. Because in this case, maybe the main program may not have been made properly or the subordinates are not done. So you have to use the driver and stub. Depending on the integration approach, it can be depth or breadth first. Subordinate stubs are replaced one at a time with the actual components, and tests are conducted at each component. This is integrated whenever the components are integrated. On completion of each set of tests, another stub is replaced with the real component. So this regression testing may be conducted because maybe new errors might have come. So when we combine various module or component, some new errors may come. So regression testing can be done. So this top-down integration strategy, it verifies major control or decision points early in the test process. So this is very important, that most of the major decision points and control, these are being checked normally in top-down integration strategy. Because all control path we have checked if you apply depth first or breadth first. The integration, there is one more type which is the bottom up. So we start with the lowermost and go vertically up. And you know, when we start with the small module or units, there may be possibility, and there is a strong possibility that the upper module, which are calling it, may not have been made. So bottom up integration testing, it begins construction and testing with the atomic modules or the unit modules. Okay. So the functionality provided by the components subordinate to a given level is always available, and need for the stub will not be there, is eliminated. Because main module you are making and you have this module, so the subordinate module is our stubs, because you are already starting with the stubs. Means the bottom most, that means we don't need stubs in this case, bottom up integration. So what are the steps? See, the low level components, we combine them into clusters. We also call them as builds. That is going to perform a specific software sub function. So these are the clusters we are making in this particular figure. I am demonstrating the cluster 1, cluster 2, cluster 3. Okay. So a driver, which is a control program, is written to coordinate the test case input and output. So this D1, D2, D3 are the drivers for 3 clusters we have defined. D1, D2, D3 is not made. Okay, so we have to write a driver here. So then the cluster is tested. That is the cluster 1. I'll just show you which cluster we made. So this 4, 1, 2, 3, 4, this is cluster 1. Then 1, 2, 3, 4, 5, this is cluster 2, which is below D2. Below D1 is cluster 1, below D2 is cluster 2, and then D3, below D3, the 2 blocks you see is cluster 3. So cluster 1 will be tested with D1, cluster 2 will be tested with D2, cluster 3 will be tested with D3. So each cluster, this is cluster 1, this is cluster 2, and this is cluster 3. So this cluster will be tested. And now the drivers which we made, D1, D2, D3, these are removed. And now the clusters are combined upward in a program structure. D1 will eliminate, D2 will eliminate, and will directly combine this cluster 1 and cluster 2 and cluster 3 with what? MA and MB. Each of the cluster is tested using a driver. As I said, you have to test a cluster using D1, D2, D3. D1, D2, D3 are the drivers. So the components in cluster 1 and 2 are subordinate to what? M sub A. D1, D2 was there, we already tested. Now they are subordinate of MA. So drivers D1, D2 will be removed, will eliminate it, and the clusters are eliminated. This interface, cluster 1 and cluster 2 are interfaced directly to MA. Similarly, D3 and D2 will be removed, and this cluster 2 will be directly fixed with MA, and this cluster 3 will MB, and finally MA, MB, because they are also, we have to do it using the possibly with a driver. And finally, everything will be combined with your final top one, MC, and need for separate test driver is less. In regression testing, what happens? Whenever we add a new module or new component in the integration testing, the software will change. Whenever you are adding some other thing, because this is one module or a component, and you are adding one more component or a module in the integration testing, because in integration testing it is all about integration, adding, but the software is changing. The software may change because of variety of reasons. It may happen that new data flow paths can be introduced, input output, control logic, this may be invoked. So these changes may cause certain problems with functions that previously was working fine, flawlessly. So regression testing is a re-execution of subset of tests already been conducted. That is, if we have around 50 tests, so we take around 20 of this. 50 already chosen, done, 20 we choose. So regression testing is re-execution of these 20 tests already been conducted to ensure that these changes have not propagated unintended side effects. Regression testing is all about checking if something has been done, some side effects are not there. So regression testing, they can be done manually, and we have a new way automated capture playback tools These capture playback tools, this is enabling the software engineer to capture test cases and result for subsequent playback and comparison. The regression test suite, that is the subset of tests to be executed. We can divide it into 3 different classes of tests. So these different classes of tests of regression test suite, as I said, these 20 we have taken, so we can again divide them. First is the representative sample of tests that will exercise all software functions. The second part or second subset will be additional tests that focus on software functions that are likely to be affected by the change, only those functions which are more likely to be affected if certain change has been done in the component or the module. And there will be third subset also, tests that focus on the software components that have been changed. You know that this software component has been changed. So these subset will be mainly eyeing upon these software components. So this regression test suite, these are the 3 different classes of test cases. So regression testing cycle contains of, first we write the regression test, then we run the regression test, then we run the test, then we find and resolve the bugs. Smoke testing. Now this smoke testing, if you can relate it with the hardware. You buy a hardware or you make a hardware and just you put the plug inside, that is in the power. And if this device works, it's okay, you have to proceed. But if you see smoke, then you don't have to proceed. That is the smoke testing. So smoke testing is an integration testing approach. This is used when product software is developed. The smoke testing is all about the initial testing, the shallow testing. So this is designed where you have a fast paced mechanism for time critical projects. So this time critical projects, here we choose the smoke testing. So software team assesses the project on frequent basis, normally daily basis. So this smoke testing, first of all, the software components that have been translated into code are integrated into a new build. Okay, so a new build is made, and these are initial builds. This is not 30th, 40th build. This is say under 10 build. So a build include all the data files, the libraries, it may be reusable modules, and also the engineered components. So these are initial builds, and a series of tests is designed to find out or to expose error that will keep the build from properly functioning or properly performing its function it is intended. That is, the basic idea is to uncover, to find out the showstopper error. That error or that particular part that is having the highest likelihood of affecting the project schedule. So we are only interested in the showstopper error, not all the error. The main error which can create a smoke or which has created a smoke. That is the smoke testing. So this is, as I said, this is not a deep, narrow or deep testing. This is a shallow kind of testing. We need to find the main cause. So the build and the entire product, which is in the current form, is smoke tested daily, as I said, frequent basis. So daily frequency of testing gives manager and practitioner a realistic assessment of integration testing progress, because every day they are testing, every build they are testing, and every day they are adding something. So this initial builds, if they are 3 builds, we do the smoke test, one of them fails. So we just discard it. We don't go ahead. The others we can do. The further testing will be done only for the other 2. That failed the build? No. Smoke testing, it has a lot of benefits, because if the project is complex, time critical project, smoke testing, first of all, the integration risk is minimized, because we are testing the software project daily. The incompatibilities, as I said, the showstopper errors are uncovered, they are found out early. So there will be less chance that the schedule will be impacted. The second thing is the quality of the end product is improved, because this approach is integration or construction oriented. So daily smoke testing will find out the functional errors as well as the architectural and component level design errors also. So the quality of the end product will be improved. First was integration risk is minimized. The third one is error diagnosis and correction are simplified. See, like all the integration testing approaches, the errors which are found out using the smoke testing are associated with what? New software increment. That is those part which has just been added. And this is the probable cause of newly discovered error. So error diagnosis is easy. Progress is easier to assess. Because every passing day, whenever we are integrating and checking, okay, what you have done today and tomorrow, if some error has come, by smoke testing we can see, oh, this error has been done because of this one. So this improves team morale and gives manager a good indicator that progress is being made. Smoke testing and sanity testing. So these two testing are very important and they are taught supplementary and complementary also. So in hardware terms, when we take an instrument or design or make or construct an instrument, when we put the plug inside, the hardware part may burn. So you'll see a smoke. So you don't have to test it further. Smoke testing is all about this. That in the initial builds, when the software is relatively unstable, I am talking about the build 1, 2, 3 initial builds. And when the software is relatively unstable. So we do the smoke testing. This smoke testing is a shallow testing. It is not deep testing. It is not that testing which goes to a particular part. Overall view, so it verifies critical functionalities like application starts successfully or not. In sanity testing, we are talking about certain stable builds. So relatively stable builds which are done after multiple rounds of regression tests. Now when the builds are stable, we verify the new functionality or some bug fixes in the build. So this smoke testing and sanity testing are done with different view on different builds for the narrow and the shallow way. And when the tests are passed, then we go for another testing. It can be system testing, it can be regression testing. Okay. So these two testing are uncovering different kinds of error. In smoke testing, first thing is that the smoke testing is performed to ascertain that the critical functionality of the program is working fine. That is, we need to find out the showstopper, that error or that problem which is going to be having maximum likelihood to impact the schedule. In sanity testing, it is done to check the new functionalities or bugs that have been fixed. The objective of the smoke testing is to find out, verify the stability of the system in order to proceed for more tests like the rigorous testing. Okay, we just whichever has problem, we'll leave it. We don't go further. The objective of the testing is to verify the rationality of the system in order to proceed with more rigorous testing. Because we are working on more stable builds. Because we are verifying the new functionality, bug fixes in the build. In the smoke testing, mostly it is performed by the developers or the ITG, independent test group or testers. In sanity testing, it is always performed normally by testers. Smoke testing is usually documented or scripted. Sanity testing is not that much documented, or you can call it as unscripted. Smoke testing exercises the whole system from end to end. So this is a broad and shallow kind of testing. Sanity testing exercises only a particular component or a part of the entire system. So this is narrow and deep kind of testing. So this smoke testing is overall health checkup of a body. Sanity testing is a particular problem encountered and going to that. For example, liver problem or a heart problem. So sanity is going to a basic part. Smoke testing is first checking overall and then finding out where the problem may be. So this smoke testing is like a general health checkup. Sanity testing is like a specialized health checkup. The test strategies for object-oriented software. So whenever we test object-oriented software, we have some testing method. like the state-based testing, fault-based testing, and the scenario-based testing. So fault, state, and scenario. So what is the testing objective? In all the testings, the objective of the testing is to, wherever you are doing what, the web app, the conventional software, mobile app, the main objective is to find out more and more errors, the greatest possible number of errors, but in a manageable amount of effort applied over a realistic time span. That is, you have to take care and keep in mind the money, the budget, the time, and the schedule. In the object-oriented context, what is the unit test or what is the unit testing? So, in unit testing, whenever we talk about object-oriented, an encapsulated class is the focus of unit testing here. Because in conventional software, we used the component or the module as the one unit. So here we have a class, and in this class we have variables, that is the attributes, and then we have functions. You can call it as procedures, operations, method, whichever name you like. So this is a whole class and encapsulating the functions which are operating on certain data. The data are variables, the data on which this function work. So the encapsulated class, this whole class, is the focus of unit testing. The operation or the functions or the method in class, these are the smallest testable units in object-oriented paradigm. Right? The functions, the operations. Because a class may contain a number of different operations, there will not be only one function, there can be multiple functions. For example, if this class, let us say any name calculator or operations. So what all operation can be there? It can have add, it can have multiply, it can have say division and many others. So a class can contain different variety of functions or operation. And a particular operation, it also may exist as a part of number of different classes, because we know about polymorphism, we know about the function overloading. So we can have this add function or any of these function in another class also. Okay, so we have to test a single operation as a part of a class. For example, if you have a class 2 and you have an add function here also, this add function has to be tested in the context of class 2, and first one add has to be tested in context of operation or the class 1, you can say. So this is the main scenario here. Let me give an example to make it more clear. For example, we have an say operation X, and this is in superclass. Say superclass is just a class. So we have a function X here. Now we have multiple subclasses. So this function X may be inherited by say class C, which is inheriting class A. So this all content of class A will come to class C. Okay. So each subclass uses this operation X, but this operation X or function X or method X, this is applied within the context of private attributes and the operation defined for the subclass. So this function, same function in both of these classes will behave, work differently. So it is necessary for us to test this operation or a function in the context of each of the subclasses. So when we did the conventional software or the traditional, what was that? Unit testing was the module, was the component. But in class testing for this object-oriented software, this is equivalent to the unit testing of the conventional software. Okay, class testing is done for operations which are encapsulated by a class, and also the state behavior of the class, because the function are going to change the data and the state will be changed every time. So method will be in unit testing and thread will be in system testing. under the integration testing in the object-oriented context, because the object-oriented software does not have that hierarchical control structure. Because in conventional way, we used to take the modules or the component and then we combine them and then we do the integration testing. That is, we have to test the interfacing. That is what we were doing. So we were using the top-down, the bottom-up. In top-down, we were using the different type of breadth search and depth first. But here we don't have that obvious hierarchical control structure. So traditional top-down and bottom-up integration the strategies are not having that much meaning here. So in integration testing, in object-oriented, we have two strategies. First is the thread-based testing. This thread is not equivalent to the thread we talk about in operating system. So what we'll do here is, we'll take certain classes and these classes are those classes, or we'll take the subset of the class which are going to respond to one input or an event for the software or the system. So these are whole classes. We took them as a subset, combined them, and then they are acting on certain input and event. So each thread, this is one of the thread. So you can have multiple thread, a subset of a class. You can have multiple classes, say 100 classes, 50 classes. So 10 you can take as one thread, 10 you can take as another thread. So each thread is integrated and tested individually, right? This thread 1, thread 2, this will be tested individually. And then we'll do the regression testing also, because when we combine certain thing, there should not be any side effect, or any change may not have some side effect. So this is the thread-based testing. This is one of the strategy of integrated testing for object-oriented. Then we have the use-based testing. So this begins by testing those classes, because let me give you an idea. There are certain server classes, there are certain independent classes, and there are certain dependent classes. There are certain dependent classes on server class, but there are certain classes which are somewhat independent. They are not dependent on a server class, because this is the independent class. It might not have any relationship with the server class, or very minute relationship. But there are certain classes which may have direct, say, interaction or dependency with the server class. So we will test first the independent class that is not having that much relationship with the server classes. Then we'll come to the next layer. And these are the dependent class, because as I said, these dependent class will be related or will be dependent on the server class. So first we check the independent, then the dependent class. This is the use-based testing. So we can use the drivers also and stubs also. Drivers are the main program calling. Stubs are the programs or sub-programs which are invoked by what we are testing. So we have a driver class. The driver can be used to test operation at the lowest level and whole group of classes. A driver, for example, can be a user interface. So if you are calling everything from the user interface, for example, in Qt, so you can make a simple user interface, not that proliferated, but just a simple interface. And then you can start or invoke your classes. And when you're calling different classes, these classes may have collaboration. So when you have collaboration between different classes and some of the classes are not being made, for example, C1, C2, C3, and C2 may not, you have not prepared it or not filled it. So you can make a stub of C2. So cluster testing is also one of the steps in the integration testing. So here we use the CRC and the object relationship model. We know how to say design or make a design of object oriented. So a cluster of collaborating classes, the idea we got from the information from design CRC and object relationship model. Now this is exercised by designing test cases that uncover the errors of the problem in the collaboration. And this collaboration is coming from where? From the design, So this is how we do the cluster testing also. So we have the thread testing, we have the use case, and one more, cluster testing. When we are working with the web apps or web applications, what happens here is, see, whichever software testing basic principles are there, it will be applied to whether you use the conventional software, object-oriented, mobile apps or web apps. Everywhere the basic principle of the software testing won't change. But the something what we need to see here is in the web app is web app is all about working on say internet or intranet on a web browser or some web services. So first we have to see the content model for web app. If there is any error, then the interface model is reviewed just to ensure that all use cases we have covered and accommodated. So this is the interface model, interface testing, because interface is very important here. The design model for the web app, this will be reviewed because the web app is all about navigation. One page, one HTML page, you're going to another HTML page like this and coming back and going here and there. So design model for navigation error problems and the user interface, because user interface is all the presentation we have and all the navigation mechanism will be from the user interface. Then all the functional component, because whatever function this web app is doing, this has to be unit tested. Each functional component, whatever work it is giving, means giving input and output. Navigation throughout the architecture is tested. That is the software architecture which you have made for this web app. The navigation throughout the architecture has to be tested. It should fulfill the requirement of the architecture. And the web app is tested for the compatibility, because this web app may be working on Chrome, it can be working on Internet Explorer, the Firefox, so different machines also. So different environmental configuration it will be working. So you have to see the compatibility with different environmental configuration also. This is very important as far as this is concerned, web app. And then the security test. When you are dealing with internet or intranet or web services, there are certain vulnerabilities, because there are people who want to penetrate. So you have to exploit these. Any attempt to exploit these vulnerabilities has to be stopped. Okay, so security test has to be done in order to feel safe. Then the performance. If the web app or web application you have developed and some performance issues are there, nobody is going to come on your web app or not going to use it. So performance test is also very important. And then you have to give it to the users, certain users, because there has to be some controlled and monitored population who is going to test your web app, because ultimate user is the end user. What are the test strategies for the mobile apps? See, all the basic principle which we use in software testing for any kind of software, it can be mobile app, it can be web app, it can be conventional software, it can be object oriented. So testing mobile application adopt the basic principle for all the software testing. But there are specialized things in mobile apps, because you are going to make the app, or you are making an app for a mobile. What is special? The size is small, the battery is little, the resources, the storage, and since the security is also an aspect, the network connectivity, network issues is a main key to understand. So what we will do is we'll have some specialized testing approaches like the user experience testing. So users are involved early in the development process to ensure the usability and accessibility expectation of the stakeholders on all the supported devices. So what is the user experience on different devices? What usability does he want, and the accessibility to other people also, normal people and those who are specially able. So you can have a Samsung mobile, you can have Android running on it, you can have an Apple mobile, some iOS running on it. Then the device compatibility testing, same thing applies here also. But this tester will verify that does this mobile app work on all the required hardware and software combination that the user has given. You are not making for everyone, but the user might have given you some key requirements. So any configuration which is being provided in under the requirement specification, the device compatibility has to be tested. Then the performance. See, there are certain NFRs or non-functional requirements like the download times, like the processor speed, storage capacity, power availability. I just told you about that. So we have to check for the non-functional requirements also. Then coming to the connectivity testing. Mobile is going heavily. The name of the mobile is mobile. So there will be different networks connectivity, web service you are going to connect. So there may be weak connection, there may be interrupted connection. So you have to test for it. Security testing, it's all about penetration by other people, because tester has to ensure that the mobile app does not compromise the privacy or the security requirement. Then testing in the wild. See, you have to test this app in realistic condition. It can be Sahara Desert, it can be Yukon in Canada, on actual user devices in variety of networking environment around the globe. So this is called the testing in the wild. And then the certification testing. Where are you going to sell or allow this app? It will come from app stores. So you have to meet the standard established by these app stores that are going to ultimately distribute it. So this certification testing is also a key testing strategy for your mobile applications. Validation testing. Validation is all about, have you made the right product? That is as per the user requirement. So as we already talked about the verification, it is all about making the product right, not the right product. Validation is making the product which is required by the user. So this validation testing, it is started after integration testing has been done. So this validation testing, it focuses on user visible action and user recognizable output from the system, because it is all about user wants what. So validation succeeds, it will only succeed when the user function or user expectation is fulfilling, that the software functions as expected by the customer you are giving. So most of the time we make the SRS, software requirement specification. So it may contain a validation criteria, and this may act as a basis for the validation testing. So there are certain validation test criteria. So software validation is all about conformity with the requirement. What are the user requirement? What is given in the SRS? Are we fulfilling it? All the use case has been covered. So a test plan will ensure all the functional requirements also, and we'll talk about the NFRs also, non-functional requirement. So all the behavioral characteristics are achieved. The software behavioral characteristics are achieved. All the content is accurate and it is properly presented. This is also a part of validation. Then all performance requirements are also attained, because there are NFRs also. So the performance requirements comes under NFR. The documentation, all the documentation is correct. Software is only not software, it is documentation also. And as I said about NFRs, usability and other issues like the transportability, compatibility, error recovery, the maintainability, this also has to be checked. So there will be a deficiency list. This will be created. If any kind of deviation from the actual requirement is achieved or is, you got it. So specification, in the specification it is not there, that is a deviation. So after you see this, acceptable to the stakeholder, there will be a plan made for resolving this deficiency. Configuration review. I'm talking about the software configuration. So what are the changes? The changes are being noted, the revision, the different version, everything, So important element of validation process is configuration review also. Audit. The things are written and maintained and documented properly or not, in order to ensure all elements of the software configuration, they have been properly developed, because software configuration is a very integral part of validation testing also. So here we do the configuration review, and it is basically a configuration audit also. So all the content you have cataloged, also work product you have cataloged, and you have the necessary detail to bolster, or you can say strengthen the support activities. This comes under configuration review. Alpha and beta testing. So first of all, this comes under acceptance testing. Now, when the developer develops certain software, how the customer will really use a program? Developer is not aware how the customers are actually going to use the program. For example, the instruction developer has given, it may be misinterpreted by the user. He may not be able to understand. There may be some strange combination of the data. Data may not be understood by the user only. Output may be unintelligible. That is, in the field, he may not understand what is the output. So for that, acceptance tests are conducted in order to enable the customer to validate all the requirements. And this comes under acceptance testing. So what do we do? because user has certain requirement, you have to fulfill it in the way he wants. When he actually works in the field, everything has to be as per his requirement, and these acceptance tests are conducted by the end user. So acceptance testing, this can be conducted over a period of weeks or months, and in these weeks and months different errors are uncovered, and these, if we combine them, they may degrade the system over time. So if software is developed for many customers, most of the time the big companies, they make software for multiple customers, multiple companies, multiple stakeholders. These are different users. Now it is impractical or impossible to perform the acceptance test for each one of them. This may not be possible because the time limit, the market, time to market, all is the requirement. So most companies, they use alpha and beta testing in order to find error, uncover error that are only possible to find by a user. The user can only find certain error which the software team or the developer cannot. For that, alpha and beta testing can be a help. That is why the alpha and beta testing has come into being. So alpha test, this is the initial test. After the system testing, the first test is alpha test. Now this is conducted at the developer side by the end user. For example, you are end user. You are in Bangalore, and there is another company to whom you have given the software. They are making it, they are developing it, and this may be in Delhi, New Delhi. So developer is at Delhi, user is at Bangalore. So the alpha test will be conducted at Delhi by the people from Bangalore. You got the idea? So here the user is going to do everything, but the developer will be standing behind, looking over the shoulder, recording the errors and what are the usage problem the end user is facing at the developer side. I hope you got the idea. Alpha tests are conducted in a controlled environment because here developer is present and the company is also developer's company. So this is a controlled environment. Whatever problem you have, he'll just fix it, or he'll tell you, no, this is that thing. But the beta test is conducted at end user side. So beta test will be conducted at Bangalore. Where? At Bangalore. By whom? By the people at Bangalore. By the company who has given you the product, the software product. Okay? Say a contract. So developer is not present here in Bangalore. Beta test is actually a live test in environment, not controlled by the developer, because in beta testing no developer is present, only the user is present. So the Bangalore people, user, are going to test without the presence of developer. So the customer will record all the problem and report to developer at regular interval of time, and after the modification the software is released to entire customer base, not only to these customers at Bangalore, maybe at Los Angeles, maybe at say Quebec. So variation or beta testing is also there. That is called the customer acceptance testing. And this is when a custom software is delivered to a customer under contract. So a custom software is given. Now user wants to accept it. Customer wants to accept it. So customer will perform certain series of specific tests in order to find error before accepting the software from the developer or the development team. This is a variation of beta testing, and that is called as a customer acceptance testing. Let us see the difference also. Alpha testing and beta testing both are acceptance testing. Okay. And the alpha testing is done by the company employees or the user at the developer side. The users at the developer side, where the developer will be present, but user will only do, end user. And the beta testing is done by the customers on the end users, where at their side, not at the developer side. Developer will not be present. Okay, so this alpha testing will be performed at a lab or a testing environment. The developer will be there. Beta testing in a real environment where it is going to actually use. Alpha testing, black box and white box testing will be used, and beta testing, totally black box testing. Alpha testing will commence after system testing. Beta testing will only commence after the alpha testing has been already done. So test run can be many in alpha testing. It can be 1 or 2, multiple also beta testing. There can be reliability and security, functionality and usability. It depends on the software also. But the developers are always engaged in alpha testing because the user is testing with the developer. Beta testing, there will be no developer, only and only the end user or the customers. Okay, because the customer is checking in beta testing. System testing. Before acceptance testing, we do the system testing. So whenever we want to deliver the software, we have to recheck, re-verify, revalidate the system as a whole. We are not talking about a software. Software may be working with certain other subsystems. It can be hardware. It can be people. It can be information coming from different interfaces, from different hardware, from different network interfaces or database interfaces. So software is ultimately incorporated with all these systems. And then we apply a series of system integration and validation test. Again we do it, integration validation test. We do it on a whole system. This is called the system testing because it involves recovery testing, security testing, stress testing, performance testing. So whenever we do certain testing, especially the system testing, there is a problem of finger pointing. That is, everyone blames on one another. That is, developers of different subsystems or system elements, they may blame each other for the problem or the error. They say, oh, I have made a very good system. The problem is in that system. So rather than indulging in this finger pointing, why not to anticipate, why not to plan, why not to test the potential interfacing problems? Because when the two or multiple systems, subsystem combine, the main problem is because of the interfaces. For example, you are making a software and you are having a serial input or a parallel input or even a TCP IP connection. Now, whenever you are interacting with a system which is different from what you have or what you have built, there may be some potential interfacing errors problem. Okay. So there are certain things we need to understand while we are doing the system testing or while we are planning for it. The design error handling paths that test all information coming from other elements of the system. What do? We make a software by designing for the software. We are not designing it for the whole system. So we need to be very careful and very diligent when we are actually designing, and also the requirement specification. So these two should have the interface issues. Okay. Tests that simulate potential errors at the software interface. Most of the time the problems are at the interface. So there has to be some tests that will actually emulate or simulate the potential errors that may be because of the system interfacing. And then we have to record all the result of these tests, because if finger pointing is there has to be something to be presented as an evidence. And then we all need to participate, all the system element, all the system subsystem people and the stakeholders involved. We need to participate in planning and design of the system test in order to ensure that software, not only the software, but the system is adequately tested. So in system testing, major we have recovery testing, security testing, stress testing. Then we have the sensitivity testing. Then load testing is also there. Performance testing is also there. So recovery testing is that will force the software to fail, and how the system recovers, we'll see. Security testing, there are certain mechanisms which are built in your software for security. Does these, deter the improper penetration in different ways? This is the security testing. And then we have the stress testing. Sometimes people also call, a different variant of this, load testing. So stress testing is now we are putting all the, load or the stress on the system, like the abnormal quantity, frequency, volume. We need to see how system behaves when we put extra pressure on the system, stress on the system. So these are different aspects of system testing. We do it all in system testing. recovery testing. Whenever we are ill, we need some time to recover. Okay, some may recover well, some may recover they may take some time. So computer-based system or the software, they must recover from the faults and resume their processing with very little or no downtime, because there will be problems in the software. Okay, so software, does it work again? How much time does it take? There are reliability, availability, there are so many issues. So system must be fault tolerant. It can be electricity problem, it can be some external device problem, there may be some fault. The processing fault must not cause the system to go down or seize overall system. Shouldn't stop, recover. For example, I'll give you an example of 737 MAX. This is the Boeing, Ultra. So there was a system here. This was a very simple software, MCAS system. And because of this problem, two, flights, they met a catastrophic end. More than 450 people died just because of this line of code. So even if something happens, it should not stall the aircraft. It should not seize the overall system, because people life, matters here. So system failure, it must be corrected within a specified period of time, because today's software, they are money making. They will create immense economic damage to the people who are the owner of the software. So recovery testing is a system test. It is a part of a system test that demands the software to fail in multiple different ways and then verify that recovery is proper or not. The system recover well or not. So recovery can be automatic. Recovery can be human also. It requires human intervention. If human is involved, then we have to evaluate, try to find out what is the MTTR, mean time to repair. And this has to be under the acceptable limits defined in the requirement and other documents. If the recovery is automatic, actually there are certain things we need to know. What are the logs, reinitialization, checkpointing mechanism, data is recovered or not, and whatever is restarted, whether it is correct or not. So these are the aspects. Okay. For example, Microsoft Word, when it fails due to various reasons, recovery option is there, that recover your document. So this is a kind of aspect we are talking about. Security testing. Security testing, the software sometimes have very sensitive information. So computer-based system which have sensitive information or which is managing very, very confidential information, it may be targeted by various agencies, people, individuals for improper or illegal penetration. So these information we need to safeguard. For that we have to do a test called security testing. No doubt the software has all the security mechanism installed or coded or designed, but we need to verify it. There can be multiple kinds of penetration. There are certain security threat issues. For example, a naive hacker, he may attempt to penetrate your software or a system just for sport, just for fun. The penetration can be as easy as this. There are disgruntled employees. They want to take revenge at any cost. They are technically equipped. They are intelligent people. So they may, get the sensitive information. There are people, good people, bad people. So they are a dishonest individual. They want to gain money. They would do it for illicit personal gain. This happens in big companies. So this security testing, it is an attempt, or we want to attempt to verify that the protection mechanism, the security mechanism, which is built into a software or a system, will actually protect any kind of improper penetration into this software or a system. If you are doing a good security testing, it has to penetrate a system. It will ultimately penetrate a system, though the time and cost is always an issue. But a good security testing will penetrate a system. So as a system designer, what is your role? What is our role? is, see, I'll give you an example. We lock our house. We put multiple locks. Not because the thief or a burglar cannot open it. Every thief, because he's a thief, he knows how to get into your house. But we put multiple locks so that we want to increase the effort of him entering. Because we want to, press him so hard. Similarly, the role of system designer is to make penetration cost more than the value of the information obtained. What he want to get, the cost of getting these information should be higher. So this is how we need to put multiple layers and do all the security mechanism. Stress testing. So stress testing determines the stability of a system, testing it beyond normal operation capacity. Stress testing is all about what the system is going to behave, work in actual scenario. Because when we are developing, we are just developing. We are not aware how it is going to pan out when it is actually in the field. So stress tests are designed to confront programs or situations or the software with abnormal situation, abnormal capacity, abnormal pressure. How high can we crank this up before it fails? We want to fail the system, and that breaking a threshold points we need to know. Essentially, the tester wants or attempts to break the program. So we have stress testing, and here we execute the demanding resource in abnormal quantity, frequency or volume. There can be multiple other aspects also. So for example, if it is there is a size issue, there is a memory issue, there is a battery issue, we would like to make it work more, stress more. I'll give an example. Test cases are designed, for example, we have hardware interrupts like trap, etc. If the software is designed for say 1 or 2 at the average rate getting the interrupt, we would like to give 10 interrupts, 100 interrupts, maybe 1000 interrupts. The input rates, this may be also increased just to find out how input function would respond. For example, Mbps, we will try to give it in Gbps. The memory, the memory is always an issue. So maximum memory and other resources, computing resources, we execute it. And in operating system environment, there is always a concept of thrashing. The processor is doing the input-output activity rather than doing the actual execution work. So we'll try to create a virtual operating system where we can see how much thrashing we can present and how does the system respond in the thrashing stress. And especially the disk resident data. Most of the time the system will take from RAM or the cache, but we would like to do it, the software to do it through disk. So as I said, this is done to find out if the product behavior degrades under extreme condition and when it is denied the necessary resources. So it is expected to gracefully degrade on increasing the load, but the system is not expected to crash at any point of time during stress testing. This sensitivity testing especially came from microbiology, field. This is a variation of stress testing. This commonly occurs when your program is dealing with mainly data, number of data, mathematical algorithms, the statistical data, the exponentials, the logarithms, all these. So sensitivity analysis is the study of how the certainty in the output of a mathematical model or system can be divided in and allocated to different sources of uncertainty in its inputs. Say we have a range which is a valid data. I am drawing a range which is a valid data. But there in this valid data, there is some point, some valid data which when it is inputted to your system or a software, it will give error or the processing will be erroneous. Also, the system will behave abnormally and there will be a profound, grieved performance degradation. I am saying there is a valid data and there is a small data in this valid data. There is a small chunk which will create issue. For this your software is sensitive. So sensitivity testing uncover data combination with valid input cases that causes instability or improper processing in your software or a system. This is sensitivity testing. Performance testing. So performance testing is a software testing process used for testing the speed. Now let me give you an example. You allow a person to run for 100 meter. Then you say run again for more 100 meter, that is 200 meter, then 300 meter. So you want to check the performance of that person. So this performance testing is testing the speed, the response time, stability, reliability, scalability, and the resource usage of a software application under particular workload. I'm not saying we are trying to stress or load. I'm just saying that at a particular workload, what will be the speed, response time? If 100 meter, we made someone to run, what is the speed? 100, 200 meter, what was the speed? What is the reliability? What is the resource usage? This is the performance testing. So it has a difference with the stress and load, okay? So speed is the speed at which the application responds. Scalability is determining maximum user load the software application can handle. Stability is determining if the application is stable under different varying loads. For a real-time and embedded system, software does not conform to performance requirement. This will not be acceptable. A real-time and embedded system has to be under certain performance requirement. We need to accept only, we will accept software only when it fulfills this performance testing. For example, 50 second, 100 meters someone is running. If it is running in 100 seconds, we will not be able to accept it. Even for 51, we will not be able to accept it. So performance testing is designed to test the runtime performance of software within the context of an integrated system. Integrated system, that is, you have a hardware, you have a software, and other subsystem. So performance tests, these are often coupled with the stress testing. As you see, scalability we just talked about. And it usually requires the instrumentation of both hardware and software. That is, we want to measure the resource utilization, for example, the processor cycle, in exact fashion. And this can be done because, as I said, we just want to see the performance. The external instrumentation, this can monitor the execution intervals, log events, for example, how many interrupts are there, and the sample machine states, how does the state change on a regular basis. By instrumenting a system, a tester can uncover situation for degradation and even the possible failure. Deployment testing. So whenever we are done with the software, we have made the software as a software developer. Deployment is, now we have to give it to the user. So deployment is the mechanism through which applications, modules, updates, and patches are delivered from the company who has developed to the company or to the individuals or to the stakeholders for whom it was being developed. So this is one of the phase in SDLC. The software may have to execute on various platforms and operating system requirement depending upon the requirement specification what the user has given you. Deployment testing, this is also called as a configuration testing. Configuration testing, deployment testing. It will exercise the software in each operating system which is being defined. So deployment testing, it will examine all installation procedure and specialized installation software. These are called the installers. We make it through install sheet, etc. That will be ultimately used by the end users or the customers. For example, Windows 10 they have given, and now we are upgrading it to Windows 11. How does it work? So we have to check the software before we actually hand it over to the user. So different configuration, different environment, we have to do the configuration testing or the deployment testing. So if somebody calls you with configuration testing, you need to answer about deployment testing. And software is not only software. It has all the documentation that will be used to introduce this software to users. But there are different documents also, like the user guide, etc. Debugging. Bug is a problem or an error. D, when we use this DE before a word, that means we want to remove it. That is, debugging is a removal of error. So the process of finding bugs or errors and then fixing them in any application or a software is called debugging. So first, finding an error, then fixing or solving the error. So why this debugging is coming? when we do the testing, what is the result of testing? Errors, bugs, problems. Debugging is all about removing this error, and it comes after testing. So we need to understand the difference between testing and debugging. Testing is the purpose, whole purpose is to find bugs and error. Debugging purpose is to correct these bugs and error. Testing is normally done by the tester, the ITG, the independent test group. But debugging is done only by the programmer or the developer, because he has to locate and then remove the error. Testing can be automated, static analysis, dynamic analysis we can do. Debugging, it can't be automated. Testing, it can be done without design knowledge, because you can do black box testing, you can do gray box testing. But debugging, you have to go inside, you need to know the code, you need to know the design of the software or the application. Then only you may be able to locate and then fix the error. So, when a test case uncovers an error, when we apply the test case, debugging is done as the next step to remove this error. So, the debugging process, how does it work? See, in test case, there is a template. We apply the test case. So, debugging process begins with the execution of this test case. And the result in the test case, what do we write? That this is the test case name, what are the pre-condition, post-condition, and then we have actual result and the expected result. All this will be there. And the exception handling. So the expected result and actual performance and the result, if they are not corresponding, then debugging will attempt to match the symptom with the cause. Then only we can go for error correction. Because if the expected is not equal to actual, then only there is a problem. So debugging may have two outcomes. The first outcome is the cause of the problem or the error will be found and it can be corrected or it will be corrected. This can be one of the debugging outcomes. Okay, this is a very obvious kind of understanding. But one very unobvious is the cause will never be found, not be found. Now you'll say, oh my God, how can this happen? But if you have really worked in the software industry, you know that there are sometimes the error will never be found. Even the error will never come again. It will not be incarnated. So debugging, see, you can find out by certain way how the bugs can be. Few characteristics of bug can give us some clue. For example, the symptom and the cause may be geographically remote. You're working on somewhere, and if it is geographically distributed, somewhere else processing is going on, there may be problem somewhere else. If you have some highly coupled design of component, this may aggravate the situation. Sometimes the symptoms just may disappear, maybe temporarily, and some other error comes when another error is corrected. Sometimes you correct an error, the symptom may disappear, but it may reappear. The system may actually be caused by some non-errors. Okay, there are certain errors which you find say that it is an error, but they are actually not errors. They are just some round of inaccuracies. But we have to decide that whether we have to accept it or not. Because if we want the latitude with the 2 decimal points, you are getting it in 1 decimal point, that may not be acceptable. The symptom may be caused by human error. That may not be easily traced. Sometimes you do some user interface work through your mouse or keyboard or whichever. It may not be traced. The symptom may be timing problems rather than the processing problem. For example, you have a system, you are getting some packets, say 1 millisecond, and the other party is sending in 100 millisecond. It can be a timing problem rather than processing problem. It may be difficult to accurately reproduce the problem and the input condition. Sometimes you may not be able to reproduce the same input condition. The symptom may be intermittent sometime, especially the embedded system that couple hardware and software inseparably. Here you see the system may come sometime, it may not be visible sometime. This may be a cause and this may be a clue. The system may be, or the problem may be due to causes that are distributed across number of tasks running on different processor. So the errors may be, say, mildly annoying. For example, you have some incorrect output data, but it can be catastrophic also. Okay. For example, if you have some latitude and after decimal you want 4 but 2 is coming. You have heard about 733 max, we talked about that. So 450 plus people died just because of MCAS system. It was a software code. So the nozzle, it will push the nozzle or the nose of the aircraft down, and without and it just gives 10 seconds for the aircraft pilot to respond. So this can be catastrophic also. So pressure sometimes, it forces developer to fix one error and it may introduce few more because the timeline, the budget is so stiff. Sometimes the developer are forced that please do it in this time. And because of the time limit, the developers, they want to fix one, but there may be some more bugs that can be introduced. So here, this is the situation of debugging. So there are certain strategies for debugging. What is the objective of debugging? Because all starts with testing. Testing uncovers errors. So first we have to locate the error and then we have to fix the error. So the objective is to find and correct the cause of the software error or defect. So this objective, how do we achieve? Sometimes we systematically evaluate it. Sometimes some experienced, debuggers, they know where it is. Sometimes it is luck also. So in order to, take all these into account, there are 3 debugging strategies which are adopted in order to find and get this objective. The first is the brute force, then we have the backtracking, and then the cause elimination. So these are the debugging tactics. Brute force. So the most common and least efficient debugging method. Brute force is like, a brooming. So this is the mostly used by everyone, but least efficient. And this brute force is applied when all other way of locating and fixing the error is not achieved. So here we adopt the philosophy that let the computer or the system find the error. So here we do everything. In the integrated development environment, for example, Visual Studio or NetBeans, memory dumps are taken. And then we put some break marks, break points, and then we'll try to find out the traces and memory dumps, traces. Along with this, we'll put a lot of these statements, printf statements at every important line. What are the result? So the memory dumps, runtime traces, and the program will be loaded with the output statements, especially the print statements. So this is how they let the computer find the error philosophy work. It may ultimately lead to success, but the effort and time will be too much. Backtracking. So this backtracking is when you are talking about a small program. Backtracking is a successful way of debugging, fairly common also. If I'll relate it with Corona, whenever some person is positive, to whom he or she has met, it is backtracked. So the cause from where this has originated in that country or region, this is found. This is the way. Same here, beginning at the site where a symptom has been uncovered, the source code is traced backward. It is done manually until the case is found. And as I am saying, it is for small programs. As the number of source line will increase, the number of potential backward paths, they will be large, actually unmanageably large. Coming to the cause elimination. So cause elimination is manifested by the induction or deduction with binary partitioning. So what we do here is we, based upon our experience, etc. For example, if file transfer we are doing and the file is received, but the size is less. 1 KB is sent, is slightly less than that. So what may be the error? So there will be some hypothesis we'll make, some cause hypothesis. It may be a connection problem, it may be some data size problem, it may be the packet size problem. There are so many things. It may be done by TCP rather than UDP, etc. So, and vice versa. So then we try to eliminate. Oh no, this is not the problem, this may be the problem. Then finally, when we eliminate all others, the final hypothesis, we keep it. Okay. So the possible causes all these are kept, and one by one they are eliminated. If the initial test indicate that particular hypothesis is showing promise, then this is how the data are defined in attempt to isolate the bug. Automated debugging. Debugging, normally a user or a developer or say a programmer has to do, go to the code, locate, and then find out the bug and then to fix it. In the integrated development environment, sometimes we have certain tools with the IDEs giving or some other help like the rational tools, like the understand tool, like the LDRA tools. So they are not automated, but they are semi-automated. So debugging tools, they provide semi-automated support. For example, the IDEs, they capture the language specific predetermined error. For example, if you don't put the semicolon, the error will be there. Some variable you have used without say defining it, then it will give you an error. So this is the semi-automated support. Debugging compilers, dynamic debugging aids like the tracers, automatic test case generators, and the cross-reference mapping tools. These are all available as a part of automated debugging, but ultimately the developer or the programmer has to debug, and these are just the support, and this can help immensely in order to locate and fix the error. So in order to correct the error, once the error is being found or the bug is found, it must be corrected. So Van Vleck, he suggested 3 simple questions that you should ask yourself before the correction that will remove the cause of the problem or the bug. So the first is the cause of the bug reproduced in another part of the program? That is, there can be different parts because there are sub-elements, sub-programs. So is the cause of the bug is somewhere else? In many situations, a program defect is caused by some problem or erroneous pattern of logic that may be reproduced elsewhere. The second question will be, what next bug might be introduced by the fix or the solution I am about to make? Because before the correction is made, the source code should be evaluated in order to assess the coupling of logic and data structure. If the coupling is more, then it may give you more errors if you try to fix one. What could we have done to prevent this bug in the first place? So if you correct the process as well as the product, the bug will be removed from the current program and may be eliminated from the future programs also. For example, the clean room strategy, the statistical software quality assurance. So these are certain questions you should ask before you correct the errors. Okay, this is all about this topic. Thank you so much. Take care of yourself.